Welcome back, mechanics students. Now we're going to plot Mohr's circle. And so, again, we want to take the stresses that are acting on an element, so normal stresses and shear stresses, and we want to be able to transform that to any orientation. So whether you're looking at it in the XY plane or you look at it slightly tilted, you'll be able to determine the stresses that are acting on this particular element. So to do that, I have this process laid out. It's going to be 7 steps, basically walk you through it. So the first step is always to figure out what stresses are acting on your cube. So we come in and we look at our cube. Now remember, the cube is part of a larger system or structure. So it involves us doing maybe statics or even structural analysis to figure out the forces and then ultimately the stresses that are acting at a particular point. But once we have done all that analysis and we can identify the stresses that are at that point, then we can go through and we can determine if failure occurs by looking at principal stresses, max shear stress. And to do that, we're going to use Mohr's circle to help identify those values. So, first step always is to do your analysis to get this cube. So I call that drawing a sketch of the element. So we come in and we'll need to identify a sketch of the element. Now remember, we're going to deal with plane stress in this class. So that's stress only in a 2D plane, in this case the X and Y plane. So we have some normal stress in the X direction, normal stress in the Y direction, and shear stress, tau xy. And the way that I've drawn all the stresses here is going to be my positive sign convention. So we're going to take tension as positive, and then this is the orientation of shear stress that is positive. Again, positive X plane in the positive Y direction, positive Y plane, positive X direction. So once we have the sketch of the element drawn and we have all of these stresses identified, then we can move on to step number 2, which is to set up a coordinate axes with sigma on the x-axis, positive to the right, and I set up tau on the vertical y-axis, positive downward. So I have tau on the vertical axis, sigma on the horizontal axis. Now I use this system because what it's going to allow us to do is that rotations, when we start to rotate our element, rotations in real life will match the direction on Mohr's circle. But we'll get there in a little bit. You might not understand that right at this second. All right, so I set that up. Next step, I want to plot sigma x and tau xy. So I go in and I say, okay, sigma x, tau xy has some value. And remember, positive tau, positive downward, and so I sketch this below the x-axis. Then I need to plot sigma y minus tau xy. So that is maybe here. Sigma y minus tau xy. I plot that point. Then I draw a line to connect them. Okay, so that's step 3. Step 4 is to locate the center of the circle and then draw the circle. So I know that since tau xy remains the same, then the center has to be right along the x-axis. And that goes back to, remember, when we derived Mohr's circle equation, we said it would have a center along the x-axis. So this is going to be our center. Then I can pull out my compass and you can stick my compass in there, or in this case I'm going to have to freehand this circle. So come in, draw the circle. Okay, does that look like a pretty good circle? I think so. I'll go ahead and move this. Sorry about that. Go ahead and move that point so we have a nice, complete Mohr circle. Circle's a little wonky, but it'll be okay. Step 5, we can use trigonometry to solve for the radius of the circle. So, on my circle, here's my center. So then this is going to be my radius. I'll label that R. So I want to figure out what the radius is. So if I look at my horizontal distance and the vertical distance, I can create a right triangle. And I need to know what this horizontal distance is, and I need to know what this vertical distance is. The vertical distance is easy. It's tau xy. The horizontal distance is a little bit harder to figure out. It's sigma x minus the center. Well, I haven't figured out what the center is. So let's go one step back and let's figure out what the center is. I see my center is halfway between these 2 points. So that's going to be the average of sigma x and sigma y. So my center will be at sigma x plus sigma y divided by 2. And then it's along the x-axis, so it's comma 0, or if you want to keep that as a coordinate, I'll just say that this is comma 0, and we'll list it like coordinates so that we see it's a circle. Alright, so then this distance must be sigma x minus this number. And if I do the math there, I'll see that this value is sigma x minus sigma y divided by 2. And if we want to do the math real quick there, we can. We could say, well, it had to be, what did we want? We wanted sigma x minus the center. So that's going to give us sigma x minus sigma x over 2. It's going to give us just sigma x over 2. Then we're going to have a negative that gets distributed minus sigma y over 2. I put them under the same denominator. I end up with sigma x minus sigma y over 2. Alright, so hopefully you saw that with the algebra. The radius here equals one leg of the triangle squared plus the other leg of the triangle squared. And that, of course, equals the radius squared. So we'll make sure we get the squared there. So we see the radius squared is equal to sigma x minus sigma y over 2 squared plus tau xy squared. Okay. I think that takes us through item number 5. Item number 6 now asks us to find the principal stresses in the max shear stress. So I want to do this visually. We can see that the principal stresses, remember, principal stresses are the maximum value for normal stresses. So where on the circle do we have the maximum or minimum sigma? I think we see that the maximum value is here, and the minimum value is here. So these are our principal stresses. This one will be sigma 1, and this one will be sigma 2. Typically, we order principal stresses in algebraic maximum to minimum. So 1 is always the algebraic highest, and then 2 would be less. There's going to be a third principal stress, but we'll talk about that later. All right, so that takes us through identifying the principal stresses, but we probably want to know how to calculate those. So I think I could find sigma 1 and sigma 2. Sigma 1 and 2 is going to equal, the value here is going to be whatever my center is. And then to this point, it's going to be my center plus, remember I calculated this radius already. I can swing that radius up here. So sigma 1 will just be the center plus the radius. And sigma 2 will be the center minus the radius. So to solve for our principal stresses, we take the value for the center, and then we can do plus or minus the radius to solve for the principal stresses. So, all right, I think that's good. Finally, we want to identify the max shear stress. So tau is at a maximum at the bottom of the circle. And its value also is going to be this distance, which happens to be the radius. So tau max equals the radius. Great. I think we've done a great job. Now we are on to step 7. Step 7, we want to use the circle to determine the orientation of the elements for principal stress and max shear stress. So on our circle, if we're at a given point for stress, remember here, to get to the principal stress, we can rotate counterclockwise to get here, and this value is going to be 2 theta p, where theta p is the angle of rotation to the principal stresses, to the principal stress planes. Okay, and we derived a formula for theta p in the last class with the stress transformation equations. And you'll see that that formula was that the tangent of 2 theta p was equal to tau xy divided by sigma x minus sigma y over 2. And so we'll see that that tangent, remember, is opposite over adjacent. Finally, we can go to theta to the shear plane. So that'll be the other direction. This will be 2 theta s. And again, we had derived previously that the tangent of 2 theta s was equal to sigma x minus sigma y over 2 divided by tau xy. All right, so that gives us the values for these angles. That'll help us determine the orientation to the principal stresses, the max shear stress. We have our principal stresses and the max shear stress. And so by drawing this circle, we are effectively using the stress transformation equations. I know you're looking at this circle and thinking it's very beautiful, and I just want you to know that I'm onto you, and I caught you looking so crazy in love, and about Mohr's circle, caught you looking so crazy in love, ooh, something like that. Now we want to solve some engineering problems using Mohr's circles, so we have a couple examples coming up in the next videos.